Hello, welcome to another Teacher Tobin tutorial. We're going to be looking at GCSE Computer Science Topic 2 and Sound, which covers 2.2.3 and 4 in the specification for Edexcel. There's quite a lot to unpick here, so I'll just zoom down a little bit and we'll get started. So I've got a simple example to go over first. The squiggly waveform there would be an analog sound signal. So if you used a microphone and you recorded into it to a tape machine, you'd get a waveform like that. Now, computers can't represent the analog waveform exactly as it was recorded, but what we can do is take little snapshots of it at greater intervals and greater amplitudes, so we can pretty much get as close as possible to the original waveform so you wouldn't notice the difference. And that's what we're going to talk about, the different permutations of that and what affects that. So for a simple example here, my amplitude, the height of my wave, I've put as a 2-bit depth. So 2 to the power of 2 gives us 4. So I've got 0, 1, 2 and 3 on the left hand side. Those are my 4 values. So this is going to be a really bad sample. It's going to sound awful. If that was the original sound, it's going to be barely distinguishable. But anyways, it's just a simpler version to get us started so we can get this comfortable with these ideas. And my sample rate or frequency, so for every 1 second, so let's say this is a 3-second sound clip. For every 1 second, I'm going to split it up into sort of 3 and take a snapshot every third of a second. Obviously, real recordings do it much more than this, but this is just for illustrative purposes. So what I might have here is that I might sort of go up and I can only sample at this point here. And this next sample is pretty much going to go to the top because I've only got a 2-bit depth. And maybe this next sample only goes here. Maybe that sample stays at the bottom. This goes up here. This one goes to the top. This one stays at the bottom. So it's or maybe that one could be at 0.1. So it's a pretty terrible sample. It's going to be pretty terrible, but it might just get the essence of what the original sound was. And we'll look at higher bit depths in a moment and sample rates as well. So a bit of jargon for you, which you need to know. 1 hertz is a frequency, is 1 cycle per second. So if in 1 second our frequency is measured in hertz. Now kilohertz is what we tend to use when we're talking about sampling, because we take quite a lot of samples now to capture an analog sound, and that's 1,000 hertz. So a kilohertz is 1,000 hertz. We've got the amplitude on the y-axis and our time in our x-axis. And let's just zoom in for a minute. That is going to be that's our sample. So this label here would be the sample interval. That's the sample interval, and the number of samples over a given time period would be the sample rate. Okay, that's the number of samples over a given time period. Now it should be noted that, I used to listen to CDs. I know people don't really do that anymore, but they were at a 44.1 kilohertz sample rate. Blu-rays would be at 96, Blu-ray discs. So that 44.1 kilohertz would be how many samples are taken in 1 second, which is a lot better than my example. So that's why CDs sound good. It's because they can take so many snapshots of that analog signal that it's almost imperceptible. Now, CDs were also at 16-bit, what we call bit depth. Okay, so my bit depth in my example was only 2 bits, which was pretty rubbish. But CDs would have up to 16 binary numbers, 2 to the power of 16, that of different heights of their amplitude that it could use, and that was adequate enough. But it would probably produce around about 65. In fact, I've got the number here. That would be the graduations in volume would be around that for 16 bits. But now it's more common to have 24 bits, and that's around 16 million. So it's far better. And when I record music in my spare time, I always choose 24 bits. And I notice I can tell the difference in the recordings from a 24-bit to 16-bit. Now at the end, when you're mastering, you might go down to a 16-bit medium. For sometimes streaming platforms demand it. But if you're using 24-bit waves throughout your process, you do notice a difference. It is much better. So we're going to look at some questions in a minute, but just before we do, let's have a look at audio file sizes, because these are typical kind of questions that you'll need to work through. So the formula is file size equals the sample rate, that times bit depth times recording length, and that will be the total file size of allocating the size of the audio recording. So let's just do a quick example. So let's say we've got 44.1 kilohertz song, and it's 3 minutes long, and it's at 16-bit depth. So imagine a CD track that's 3 minutes long. It's sampled at 44.1 kilohertz. It's 16-bit amplitude, bit depth, and the duration is 3 minutes. What's the file size? Okay, 16-bit, and the sample rate is 44.1. So for every second, 44.1 thousand. The formula is going to be sample rate 44.100. Let's do it in hertz, times by the bit depth, which is 16, and then times by what's 3 minutes in seconds. It's going to be 180 seconds, right? So and it's very often with Edexcel that they'll ask you to do expressions rather than, you won't need to calculate this. You don't have a calculator available, so you'll need to write an expression. So that's all very well. That's our file size. But typically questions will be a little bit more annoying than that. They might say, what's the file size in megabytes, for example? and then we've got to figure out to convert it into megabytes. So how do we do that? I'll tell you what, let me just move that over here. So what is our sample in megabytes? Well, we've got bits so far, because we're dealing with bits, and we know that 8 bits equals 1 byte, and we know that a kebibyte equals 1024. And if we did 1024 times 1024, or you could say it as 1024 to the power of 2, we get our megabyte. And you've just got to memorize these. You've just got to memorize them. If you don't, you're going to get in trouble. You memorize that. 2 to the power of 10, okay, in our binary in base 2. 2 to the power of 10 to 1024. That's a kebibyte. So we're going to we've got a numerator sorted, but what's going to be underneath? We've got to make bytes out of it, so we've got to divide by 8 because we've got bits so far, and then we've also got to factor in the megabytes. So this will be 10. The easiest way to do it would be to 1024 times 1024. Okay, you don't need to calculate the thing, but you will need to write the expression, and you'll need to know that that's a kebibyte. And remember, I think of M as million. That's how I remember it, like a megabyte, 1 million. Got your 6 zeros, and a kilobyte is 1,000, right? Like kilogram, kilometers. But obviously that's metric and denary. When we're dealing with the actual numbers that are happening on the computer, they're all base 2 because the computer works on bits, which is base 2, zeros and ones. So the actual storage is going to be measured in kebibytes, right? Which makes sense. It makes sense to understand what these things are, and then you just keep on adding zeros for the giga and tera versions of that. Okay, but that's the key, is to remember the 1024. So let's have a look at some. Let's have a look at some questions, shall we? Let's do this one first. They're all pretty tricky, annoying questions, but that's why I want to show you now so that we can tackle them. All right, so what have we got? The bit depth is 4, and it says 2's complement is used to represent the sample values. Interesting, okay. Now, technically speaking, in Edexcel, that you don't need to know about the size and magnitude of 2's complement and how the bits work and the most significant bit. But I think it's really difficult to answer questions like this and understand how 2's complement works without knowing what the most significant bit is. So I'm just going to sort of expand on this. Right, it's saying that's in 2's complement. So normally that would be 1, 2, 4, and 8. But if it's 2's complement, what we'll be doing there is saying that that is minus 8. So minus 8 plus 4 equals minus 4, plus 2 equals minus 2, plus 1 equals minus 1. So that number is minus 1, which is that down there. Okay, so what it says, okay, let me read through the question first. The sound is recorded with these settings. Sample rate's 24 kilohertz. Great. Bit depth is 4-bit. Hence the 4 bits. 2's complement is used to represent the sample values. The 3000th sample of the sound is represented in binary as 1111. Draw an X on the graph to plot the value of the 3000 sample. So you just need to mark one thing on the graph, but you obviously need to first of all know where to position it. So we've got a clue already because we worked out what the 2's complement of this number is. -8 plus 4 plus 2 plus 1. Build it back up with the positive numbers. We know it's -1. So we've got to have it somewhere down here. Now, this is 1 second. And the sample rate, 24 kilohertz, is for 1 second. So the easiest thing would be to do is say, okay, what is 24,000 divided by 3,000? Oops. And you can quickly remove the zeros. 24 divided by 3 is 8, isn't it? I use a better colour. And you'll notice here 1, 2, 3, 4, 5, 6, 7, 8. So the 3000 sample is going to be here. And we've already identified that it's got to be on -1. So therefore the cross, or whatever mark you put in, draw an X. Yeah, it literally says that, draw an X on the graph to plot the value. So it will be, I mean, let me draw it in a better place. Oops. They'll know what you mean if you do it there. My iPad's not as accurate. So that would be the answer there. And it's annoying, it's only 1 mark. Oh, hang on. No, it should be more than that. It's 2 marks. Okay, fine. Yeah, 1 for that, 1 for that. And the second part of the question is, state the reason why decreasing the sample interval improves digital representation of the sound wave. Yeah, I mean, if you decrease the sample interval, that's the sample interval right now. If we decrease it, that we're adding more snapshots in, aren't we? Let's say it was 48 kilohertz, then it would look a bit like this, wouldn't it? And we'd have double the amount of snapshots on our sound wave. And incidentally, DVDs and video formats use 48 kilohertz because it matches nicer with the sample rate, frame rates, cameras. Cinema might be 24 frames per second, and 48 kilohertz works better for editing. So for video and audio are slightly different mediums in that regard. If you ever looked at in a DAW, like Logic or GarageBand, and seen 48 kilohertz in there, what's that for? It's for video. Right, hopefully that was relatively okay. I mean, it's kind of fiddly, isn't it? You have to understand 2's complement. You have to know what bit depth is, sample rate, that hertz is in seconds, cycles per second, and we've got kilohertz, 24 kilohertz cycles per second. But because it says 1 second, it gives us a clue there. Right, let's have a look at this one here. All right, a baby monitor uses a microphone to record sound. An analog to digital converter, or ADC, is used to change the sounds received by the microphone into a form that can be processed by a computer. Okay, analog to digital. Complete the diagram to show sampling frequency and label both axes. Okay, it's not too bad then. But you've got to know that this y-axis is amplitude. That's amplitude. And you've got to know that that's time on the x-axis. Right, so I would label the x and y-axis, and because I mean it's a nice 3-mark question. It's not that difficult actually, to be fair. And then how many snapshots? It doesn't even tell us the frequency of it, does it? I mean, let's say we took a snapshot here, like this, whatever that would be, is the sample interval. right? So if we took a sample there, we had another one here, whatever it is, that's the sample interval. And it hasn't asked us about complete the diagram to show sampling frequency and label both labels. Yeah, so I think that would be enough. If you put, to be fair, it's not a great question. It's pretty ambiguous about this idea of frequency. So just make sure that if you put a snapshot in, that it's smaller than the wavelength itself. Okay, let's look at the second part to this question. State the advantage of using bit depth of 16 rather than a bit depth of 8. Okay, so our amplitude is also dealing with bit depth. And if we've got an 8-bit number, it's obviously a lot smaller than having 16 bits, which we can have a much greater range in there. A 2 to the power of 8 is only 256, right? But if you 2 to the power of 16, it's going to be magnitudes more. I mean, it's going to be what we talked about earlier. The difference is pretty measurable. And then if we went to 24, then we've got 16.7 million. A bit like when we were dealing with bitmap images, similar. So the amount of graduations in volume dramatically increases then. There's a big difference between 256 and 16-bit audio in that regard. So I mean, if you're using old retro game consoles, might get away with really low bit rate samples, and they might sound good actually because they're kind of crunchy and distorted for aesthetic value. But if you want fidelity, you really need to be going minimum 16-bit and 24-bit. Also noticeable difference in graduations volume to a point where you can barely notice the difference between the original analog signal. Okay, let's look at another annoying question. An analog sound is represented in digital form. The sound is 1 second long and is sampled at 10 hertz. That's important because we know that hertz is cycles per second, right? So there are 10 cycles per second. 2, 3, 4, 5, 6, 7, 8, 9. So that's going to help us already. The digital representation has a bit depth of 5. Okay, so the bit depth is going to be literally 5 bits, and it's also stored in 2's complement. So this is the sound data here. Draw a graph to represent the data sampled. Labels for X and Y. So this is a 6 marker. This is quite a nice 6 marker. Then we can get 6 marks out of this if we play our cards right. So we've got, I might have to zoom out a little bit. In fact, how about I move this up there? It's going to be easier for us, isn't it? I'll move this sort of across a little bit. I think we can work with that. Better. So obviously, amplitude is our y-axis and our time is the x-axis. So already we got some marks. It's a 6 marker. That's probably going to be 1 mark, I'd imagine, if you label it. Maybe 2. It might be 2. I think the labels will be 1 mark and the values are going to be another mark. Okay, so let's have a look at it. That's a 0, isn't it? So we've got to have, I'm going to use a different color here. We've got to have 0. And 2's complement. So again, it's this 1, 1, 1, 1, 1. So if we said that that's worth 1, that's worth 2, that's worth 4, that's worth 8, that's worth 16. But because it's in 2's complement, it's representing a minus number signed integer, right? So minus 16 plus 8 is minus 8, plus 4 is minus 4, plus 2 is minus 2, plus 1 is minus 1. So that equals minus 1. And again, like they're not going to, in the new specification for Edexcel 2020, they don't expect you to know that. They're not going to test you on it. But I find it really difficult for you to for students to understand how two-groups complement works without showing that. So that's why I'm showing it to you. Not that you're going to get tested on that, but if you don't know that that MSB is a negative number, it's going to really throw you off when you have a question like this. So there we go. That's minus 1. So we can say, we can label that minus 1. All right, we can label that minus 1. And we can label that plus 1. But that's enough there, because this is plus 1. Okay, 0, 0, 0, 0, 1 is 1. If our MSB is 0, then it's a positive number, isn't it? And we've got a 1 there. So we've got a 0, minus 1, and a 1. And we said that we've got 1 second. 1 second. So let's divide it up into 10 things. Just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so because it said it's 10 hertz. So that means 1 hertz is a cycle per second, 10 hertz, so it's 10 cycles in that second. So what's the very first value? 0, 0, 0, 0, 0, 0. So that's going to be the very first, let me use a different color. That's going to be the very first sort of marker. Then, so we can sort of draw a line over there. What's the next one? Minus 1. So it's going to go, let's go over here. Just to make this a bit easier to see. So let me just mark the points in there. So we've got another one at minus 1, then another one at minus 1, then another one at minus 1, then another one at minus 1, and then another one at 0, and then another one at 0, then there's one at 1, another one at 1, and another one at 1. So 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 in total up to here, okay? So let's just sort of connect these together. They're going to be connected together. That's going to go down there. That's going to go up here. Those are going to go across. That's going to go across. That's going to go across, and that's going to go across. So that's our sample there. Yeah, I'm pretty happy with that. There's quite a lot to unpick there, quite a lot of techniques. You've really got to understand this particular subject in order to do that one. Let's have a look at one more. Construct an expression to calculate the file size in megabytes. Right, we did something similar to that earlier, didn't we? Of a CD quality 44.1 kilohertz, bit depth of 16, 2-channel stereo soundtrack that is 4 minutes long. Okay, so the word there which is causing me some concern is stereo. So we're going to have to come back to that. I think we're probably going to have to do something twice. So we knew that file size equals sample rate times by the bit depth times recording length. All right. Before we start converting to megabytes, let's just get the file size and then we can do the conversion to megabytes. So the sample, we know the sample rate, don't we? The sample rate is 44.1 kilohertz. So you could write it as 44.1 times 1,000, or I guess you could just write it like that. Either are going to be okay, and then times by the bit depth 16. And the recording length is interesting because it's going to be stereo, which is 2. There's 2 tracks, one for the left hand side and one for the right hand side. So 4 minutes is 4 times 60 times 2, okay, because 60 seconds is 1 minute, 120, 240, but we've got to times that by 2 to be 480 because it's stereo. All right, so gonna have to have things like that in there. Gonna have to have things like that in there. So again, it's going to be times by that, and underneath, then we can convert it into megabytes, which is what we did earlier. So we know that 8 bits in a byte, so we're going to have 8 in there, and then we need to convert it into megabytes by doing 1024 to the power of 2 or 1024 times 1024, knowing that a kbyte is 1024. Okay, so because it's got like a million, it's got 3 zeros on it, but it's on base 2, it's not metric. We've got to have the 2024 times 2024. If you're doing anything bigger than that, gigabytes, tebibytes, etc., then you just keep on times in 1024. All right. That would be enough. That would be enough to give you your 4 marks there. But if you didn't have this stereo bit might mess you up. So if you didn't put the 2 in there, you probably would lose a mark. Probably. Which is a bit mean, but you gotta just watch out. You've got to watch out for that, and it's very typical that it'll ask you to construct expressions for these things. Anyway, there's a lot to unpick there. You're guaranteed to get a question in the exam on it. Hopefully it's not going to be a crazy one, but if you've gone through this, I'm sure that those techniques will help you, and if they do help provide clarity, let me know in the comments. If you want more things like this, let me know in the comments, and see you next time.